Hi, welcome to the Chico Math Lab, and we will continue the talk about the applications of the Taylor polynomial. So this is our second set of the practice problems. We're going to approximate the log functions by the polynomial. And for the first set, we have two videos. We talk about the exponential function and the trig functions, and we do the Taylor polynomial, and where we can do the center, those things. All right, so for the log functions here, before we even take a look at the problem, that's kind of like a refresh of memory. So remember, this is the list I show you was the kind of the most useful and the most frequently used Taylor series expansions here. So for the practice set number one, we took care of when all this function, the radius of convergence is infinity. And that's kind of the easy, right? So you can just substitute the number into your polynomials. And of course, if you want to center the polynomial at a certain number, sometimes we'll make it converge to the true value function a lot faster. So now, today, this ones here we're going to talk about is how about my radius of a convergence have a fixed number. So for example, like in the log function, the radius of the convergence is 1. So what's that mean? What is that going to play in our approximation, and how is that going to affect my error bounds here? All right, so here this is the similar like the refresh memory about how do you do the Taylor polynomial expansion, and what is the Lagrange upper arrow bound for the Taylor, or some books say it's the Taylor inequalities here. So, okay, so now we're going to do two problems here. So these two things here is we're going to approximate the following value by using the first four non-zero terms in the Taylor polynomials. And then we're going to find the Lagrange upper bound for the Taylors here. So these two things here, one is the natural log 1.5, and other is natural log 2.5 here. All right. So let's see, how do we do this here? I'm going to go to the whiteboard now. Okay. Okay. All right. So so let's take a look. The first thing here, if my function f of x is equal to 1 over x. I'm sorry, if my f of x is equal to the natural log x. And I really cannot do the Taylor expansion with the center at the zeros, right? So for the Taylor polynomial, and in here, we really cannot center at a 0, correct? The reason why is because the natural log 0 is undefined. So now I want to find the natural log 1.5 and the natural log 2.5 here. So let's try to find, okay, so since I cannot center at the 0, so I need to find other numbers I can center at. And one of the things here, you want to center at something with no value. So let's say, how about I want to center at 1 here. Why is 1? Well, because the natural log 1 is equal to 0. It's a lot easier. And so let's take a look at how do we do that center at 1 here, right? So when we center at 1, so basically you just, first things here, let's try to find the functions here. So it's n is 0, 1, 2, 3, 4. Let's say 5, and this is your derivatives, right? And then here, this is you center at 1. So in here, right, you put 1 here. All right, so the first function is the natural log x. So you center to 1 will be 0. Then the next one here is just 1 over x, the derivative of natural log x is 1 over x, you put 1, so this is 1, and the next one here is 1 over negative 1 over x squared, you put 1 in, so it's negative 1. Then the next ones here, this will be 2 to the x to the cube, right? So this will be 2 to the x cube, and then you substitute the 1 in, so this will be 2. Then this one here will be negative 6 to the x to the 4th. When you substitute that 1 in, what you're going to get? You'll get a negative 6, right? Let's look one more. When the 5, what you can have? You have the 24 over x to the 5th. So when you substitute, you will get a what? 24. So now I know I can put this function in the polynomial and with the center at 1. Okay, so the first thing is here, natural log 0. So it's 0 plus the first degree is 1, right? And 1 times what? 1 times x minus 1. Okay, now the second one is here, the n equal to 2, then I need to minus 2 factorial, so it's 2. And the reason why it's a minus is here, right? Because I have a minus here. And so it's 1/2. And what is here? This is x minus 1 to the what? To the square. Correct? Okay, now the third one's here. So the third one's here, I'm going to have plus, supposed to be the 1 over 3 factorial. And then here I have a 2's here, right? So times 2, then times x minus 1 to the third. And these two, I can simplify that to what? I can simplify to the 1 over 3, right? So here I can put this is 3 here. Okay, so then the next one here is minus 4, right? So because here is a minus here, then I have a 4 factorial, and then I have a 6 here. Then here is x minus 1 to the 4. And also this one's here, what I can do here, this one, I can simplify to what? I can simplify to 4, right? So this one I can simplify to 4, so I can put it down here. All right, so now I will see that what the next one I can see is x minus 1 to the 5th over 5, and All right, okay, so now let's take a look here. We know the natural log function, the radius of convergence r is equal to 1. The radius of convergence is equal to 1 here. Okay, so now let's take a look at this one first, the 2.5, all right? So I expanded here, looks here, I expanded the center at 1. So 2.5 is here. This is 2.5. So what is the distance from here to here? What is the distance here? Is 1.5. So it's greater than my radius of convergence, right? So let's take a look. What's that mean? You know, if you find the value outside the radius of convergence, you know, so what that means, so can I use this expansion to estimate a natural log 2.5? Well, let's see here. Okay, so let's see here, we say natural log 2.5. Right, so the natural log 2.5, I can just plug that one in, right? So let's see here. So if for the first non-zero terms here, right? So the one has for non-zero terms, so it's 1, 2, 3, 4. Those are the 4 non-zero terms I have. So the first terms here will be what? Is the natural log 2.5 will be very close to, so it will just be the 2.5 minus 1. So it will be 1.5, right? Then the next terms here, I will say is very close to, so it will be this 1.5 minus 1/2. then this is 2.5 minus 1, right? So it's 1 minus 5 to the square, right? So I will get this is 0.375 here. Okay, now let's take a look at the next terms here, 2.5, right? So that means you need to add, so it will be 0.375. You add 3, so this is 1.5 to the what? Third powers, correct? So this will be 1.5 to the third power, and your values here is get 1.5. Now let's take a look at 2.5. If you add one more term, so it's minus, right? So the last terms here, so it will be 1.5 minus, right? So you use this 1.5, move over here, so it's a minus the last term, so it's a 4. So this is 1.5 to the fourth power, and then you will get is a 234,375. Let's take a look at one more term, see what happens here. Obviously, I did not see any consistent pattern or going to show is a convergence, right? Okay, so the next terms will be 0.234375. Then my next term will be 6, the 5, right? So it's 1.5 to the x minus 1, so 2.5 minus 1 is 1.5 to the 5, so to the fifth power, correct? So to the, I'm sorry, to the 5. So what is this number? It will be 1.753125. So as you can see, the number is jumping upside down, right? So we did not see any the pattern showing convergences here. Right? So I know if I want to estimate natural log 2.5, I cannot use the LNX center at 1. It's not going to work. Right? So it's not going to work because as you can see, if I put this one back to this and my values jump up and down, up and down. So the reason why is because 2.5 is outside the radius of convergence here, right? So we know the radius of convergence here is equal to 1, so has to be here, and it's outside. That's why you cannot use it. Okay, so it's not every number you can use it because it was restricted by the radius of convergence here. Okay, so this is the natural log 2.5. Then we will see what we can do about it, all right? So we'll come back later. Now let's take a look. Now, maybe I still have plenty space here. Okay, now let's take a look. How about I want to do okay, so how about I want to do natural log 1.5, okay? So the natural log 1.5 is in here. 1.5 is in here, right? So this is 1, this is 1.5. So the radius, so this radius, the radius here is only what is 0.5. So it's inside the radius of convergence. So I expect it going to work. Okay, let's take a look here. So the first things here I will say, all right, I'm still using this log expansions, right? So all right, let's take a look here. All right, so when the n equal to 0 is not going to, the work here, so it's 0. So let's take a look at 1.5, the first, the x minus 1 term. So the x minus 1 term, so this will just be what? It will just be 1.5 minus 1. So this will be 0.5. All right. Now the next terms here is 1.5 will just be the 1.5 minus 1. Now you have a second term minus 1/2. Then this is 1.5. So this is 1.5 minus 1 to the square. All right, so let's see. So this is a 0.375 here. All right, now let's take a look at the next ones here. Next 1.5. So will be 1.5 minus 1 minus 1/2. This is 1.5 minus 1 to the square, then plus 3. So this is 1.5 minus 1 to the third. Okay, so you put it into the calculator, it will give you 0.4166666 continue, right? 6 is continuous here. Okay, now let's take a look at natural log 1.5, the last non-zero term. So it will be 1.5 minus 1 minus 1/2, 1.5 minus 1 to the square, plus 3, 1.5, 1.5 minus 1. Okay, so it will be 1.5 minus 1 to the third power, then minus 1.5 minus 1 to the fourth power and the 4. So if you put it into the calculator, this will give you 0.4010416666. All right. Okay. So now, if if you put the natural log 1.5 into the calculator, let's see what is the true values for that. So here, let's see here. Let's see the natural log 1.5 here. All right. So the natural log 1.5, it will be 0.405465 1081. Okay, so that's what you put into the calculator. Okay, now let's take a look at our arrow term like we always do. So the first one's here, right? So the first one, the arrow terms here, will be what? You use 0.5 to minus 0.40. So the arrow term is 0.0945 3489. So it's not bad at all, right? You just use the linear term. It's very close to the second decimal point. That's amazing. All right, let's take a look at this arrow terms here. So if I only use 2 terms, so this arrow term is what? So you use this 0.375 minus the natural log of 1.5, you will get a 0.0304651. All right, so it's getting smaller. Now let's put this ones here. So what is this arrow terms here? The arrow terms here, you will be the same one. You use 0.4166 minus it. So this arrow term is going to be 0.01120,155. Right, so it's getting smaller. Okay, so how about if I use 4 non-zero terms? So what is here? So the arrow terms here is getting better, will be the 4.42344 to the what? To the 10 to the negative 3s, right? So you can say it's 0.004423. Okay, so now this is the one. Okay, so now we say, okay, what is the up arrow bound here? All right, so let's figure out what is the up arrow bound. So remember, right? So in here, okay, so we use the first 4 non-zero terms. So this will be my what? This will be the fifth one will be the bound here, right? Okay, so let's take a look. So my fifth derivative of x. So what is my fifth derivative? Oh, here is my fifth derivative here, right? So it's 24 over x5. Okay, so it's 24 over x to the fifth power. And now, what is my x value? my x is centered at 1 to the 1 point, the polynomial is centered at 1. My x value is 1.5. So my x is somewhere, anywhere between 1 and 1.5, right? So now, because the x is on the denominator, so I flip it. So this is 1 over x, and then will be greater than 1 over 1.5, less than 1. Then the fifth power, so then the 1 to the fifth power is greater than 1 over x to the fifth power, all right? So it's 1 over x to the fifth power greater than 1 over 1.5 to the fifth power. All right, so now I know this is less than 1, right? So this is the greatest value here is 1 to the fifth power is 1. So my m value is what? My m value is the 24 over, right? So over 1 here, right? So the 24, 1 is right here. So 24 times 1 is here. So my m value will be the 24 times 1. So it's 24 here. All right, after m's here, okay, after I have the m, so what is my bound here? My bound will be your m is 24 over what? Over m factorial, right? So it's 5th factorial. Then whatever your value is 1.5 minus 1 to the what? To the 5th, right? So if you put this into the calculator, then this will give you 625 to the 10 to the negative 3. So this is 0.00625. So if you compare what we have here, so you know with our calculation is correct. So this is the upper bound, is the third decimal is 625. And this is the true arrows by using the 4 non-zero terms. This is 0.004, so this is 4. So we know this is the smaller than my upper bound. So this is 0.00625 is the largest error you can have. So I know this is how do we find the Lagrange, the upper bounds here. So I know for this ones here, the natural log 1.5, I can use the Taylor polynomial center at 1. So while ago we said, how about the like 2.5 here? It doesn't work, right? Because it doesn't have the conversion patterns here. So how do I do the 2.5 here? So for the 2.5, so in order to be in the convergence patterns here, you can choose where is the 2.5 will be within the plus minus 1, the radius layer. So let's take a look at n. So I have a 0, 1, 2, 3, 4, 5. All right, so now I will take this is my derivatives, right? So this is natural log x, so it's the same thing again, right? So here, 1 over x squared, then it's 2 over x cubed, and the negative 6 over x fourths and 24th over x fifths, right? But now, what I'm going to center to? Well, because it's 2.5, so I think I'm going to center at 2. Or you can center at 3. You can center 2.5. You can center at 2.1 or 1.9 as long as the radius is less than 1. So to simplify, I center at 2, right? So then my first value is natural log 2. So what is this one? Is 1/2, right? So what is this one? Is negative 1/2 to the what? Square. So what is this one? Is 2 times 1/2 to the third. What is this one? Is negative 6 1/2 to the fourth. This one is 24 the 1/2 to the fifth here. All right. So you can do 3, you can do 1.9, but I think the 2 make the calculation probably is a little easier. Okay, so now Okay, so now this will be the, so now let me try to write the f of x here right now. So the natural log x right now, I can do the expanded center at 2. So my first term will be natural log 2, all right? Then plus 1/2 x minus 2. And then minus 1/2, right? So it's 1/2 to the square, then x minus 2 to the square, then plus 1/3, just like before. Right now, we just have this extra constants here, right? Okay, so now this is 1/3. This will be 1/2 to the third, then x minus 2 to the third, then what is the next one is a minus, right? So it will be minus 1/4, not 1/4, right? And then I have 1/2 to the fourth power and x minus 2 to the fourth power and plus 1/5. All right, then this is 1/2 to the fifth, then x minus 2 to the fifth power, then dot, 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 dot. So take a look, it's very, very similar, right? Like this one's here, right? So 1/2, 1/3, 1/4, 1/5. The only difference is here because it is center at 2. So this is the center at 2, right? So that's why I have those constants with us, right? So those are my constants here. Right, so those are my constants here. That's the actual constants because of the center at 2. Okay, so now let's see. After we do that, is the 2.5 going to work or not? Okay, so now let's see, is my 2.5 going to work? So let's see that. Okay, so the 2.5 here. All right, so the first one's here. So let's see here, the natural log 2.5. So the first terms here will just be the natural log 2. All right, so this will be just be the natural log 2 here. All right, and then this will be similar to that, close to, so it's a -1. Okay, now I'm using the first 4 like the others here, right? Let's see here. They say the first 4 non-zero, so 1, 2, 3, 4. I'm stopped here. All right. Okay, so the next one's here, so it will just be the natural log 2 plus 1/2. So what is my x? X is 2.5 minus 2, right? All right, so this one here will give you 0.9431471806. All right, so the next ones here is 2.5, will just be the next term, natural log 2 plus 1/2, 2.5 minus 2. Then I have this minus, right? So it's a minus 1/2 to the square. Then 2.5 minus 2 to the second, right? Okay, so in here, I calculate it will be 0.9118971806. Okay, so my last terms here, right? So let's see how close this one, if I use the 4 non-zero, so it will just be the natural log 2 plus 1/2, 2.5 minus 2, and minus 1/2 to the square, 2.5 minus 2. Now I add the last one, so it's 1/3. So this is 1/2 to the third power, and the 2.5 minus 2 to the third power. Then I put it into the calculator. I will get a 0.917 1.055.135 something here. Okay, so now if I put the natural log 2.5 into the calculator, let's see what do we have here. So natural log 2.5, if I put it into a calculator, will give me is the, oh, I shouldn't put it here, block my way. Let's put it here. Natural log 2.5, it will give me the 0.91629 07319. All right, so now we can find the error terms here, right? So the error terms for here, if I just use the constants, what is my error? So the error is pretty big, so it's a 0.223143. You just use natural log 2 minus this 0.9162. So it's 223143.5. Okay, so how about what is the error terms here? I just use 9431 minus natural log 2.5. Well, the error is getting a lot smaller. It's 0.0268564. Now let's take a look at this term, the error terms here. So you just use 19911.897 to minus natural log 2.5, right? So this one will give you 0.0043955. Wow, it's already to the third decimal point. Okay, let's take a look at these ones here. Then these ones here, the arrows here will be equal to 0.000A1478. A1478 here. All right. So this is the, if I use 4 non-zero terms here, that is, that is the, what is my arrow to the exact function value. Okay, now let's take a look at Lagrange, the arrow bound here. Okay, so since we use all the way to the third, right? So this will be my next terms, right? So it will be what? It will be the derivative to the fourth derivatives here. All right, so let's take a look. So this will be my fourth derivative for the x. So the fourth derivative, you take the absolute value is really just the 6 to the what? 6 to the x fourth here, right? So the same things here, my x, because right now is center at 2. So x is between greater than 2 and less than, where 2.5, that's what we try to find. Right, so then if you flip it, so 1 over x will just be greater than 1 over 2.5 and less than 2, 1 over 2, right? Now the x to the fourth here, so in here, then the x to the fourth will just be what, 1/2 to the fourth, right? And then greater than 1 over 2.5 to the fourth. So, so this one will give you the largest number. So now you have a 6 here. So what I have here, so my n is equal to what? So my n is equal to the 6 over 2 to the what? 2 to the fourth, right? All right, so this is the 6 to the 2 to the fourth here. So now, okay, so now let's try to take a look at what is my upper bounds here. So my upper bounds here will just be the m, and so it's 6. Right, so it will be 6 to the 1 over 6 to the 2 to the fourth over what? It's 4 factorials, right? Then here this is 2.5 minus 2 to the fourth power. And if we do the calculation, this one's here, the bound will be 0, 0, 1, 6, 2, 7, 6. Okay, so the bound will be pointer 0, 0, 0. All right, so the bound will be pointer 0, 0, 0, 976, 976, 56. So you compare. So you see here, hey, this is the fourth decimal is 8. And the fourth decimal here is 9. So I know it work out good because this one is bounded by less than this is the upper bound. So my upper bound is 0.009. So that means the highest error you can occur by using the four non-zero terms. The upper bound error be 0.009765, and my fourth, I use fourth term, the error is 0.0008148. So we know we did it right. All right, so that's it. So that's basically we try to, so like a student frequently confused, said where I need to do the Taylor polynomial centered what number. So like in here, right? So obviously centered 1 is a good choice. But then the things you can estimate, and then you need to worry about it. So this is why we said that this radius of convergence is very, very important, right? So the value you can estimate has to be within the radius of convergence. So like here, the first time we showed why the 2.5 doesn't work by using the center at 1. So you need to choose the different centers here. The different center maybe make the calculation a little bit tedious, but it will work. All right, that's it. Okay, so for the 3 videos, we covered the where the radius of convergence play in the Taylor polynomial when you try to do the approximation of the function values here. All right, that's it. I hope you guys have a pretty good understanding about this. All right, okay, and we're looking forward to talk to you in our next topics here. Okay, bye-bye.